Alright, so first off, we're going to talk about something called quadratic modeling. So we're going back to quadratics, and they will always look like ax squared plus bx plus c. So in this case, we're going to be thinking about projectiles. So the first kind of example or the modeling that we see is that we'll have an upside down parabola kind of like this. And then on your graph there are some important points like there and there. So you picture your cannonball or your arrow or whatever is being thrown up kind of following this parabolic path. So here's the first example. Let's have a parabola, or let's have a projectile that's being just thrown. And this is the equation. Now you notice that they use t's instead of x's, but they're interchangeable. The reason we use t is that t is going to be seconds. Okay, so the first question is, if this is the model of our parabola, we want to know, first of all, how high did it start? Okay, so if you're thinking about your picture, it's going to be upside down, and it's going to kind of go like this. We want to know what that point is, and this is the y-intercept. If you remember, at the y-intercept, x is always 0. So we're going to let t equal 0 here, and we're going to plug that in. So y equals now, that just means that our y is going to be 3. Now we knew that already because we knew that your c is always going to be your y-intercept. So this guy right here is your starting point. This means that it's going to be starting 3 feet up. So maybe someone's throwing it, and when they release the ball, it's 3 feet up. Okay? So the second question, question B is, when did it hit the ground? Okay, so T stands for time, and then that means this y over here stands for our height. So when did it hit the ground? That's when we have this point right here. That's called an x-intercept. And at the x-intercept, the height is 0, or the y is 0. Okay, so we would set y equal to 0, and we would have an equation to solve. Now the question is, when will that all equal 0? Alright, so I just want to pull up something I pulled up a little earlier. This is kind of what's happening here. I have my parabola. We have a starting point of 0, 3, and I'm going to have GeoGebra Desmos just figure out the answer. We should get about 1.385, okay? So going back to my notes here, how would I solve this? Well, we could try factoring. And if you remember, to factor this, we would do a times c, and you'd think about negative 48. What pairs go into that and would add up to 20? Well, we're going to have trouble with that. It actually turns out that no pairs will work. So we have to use the quadratic equation. X equals the opposite of b Alright, so this is why we practiced all these different things here. Like the quadratic, we might have to do this to find our zeros. Alright, so let's try simplifying this. I know this is going to be 400, and because of minus, and this is a minus, this is actually going to be adding inside. 3 times 16 is 48. 48 times 4 is 192. all over negative 32. So our answer is going to be negative 20 plus or minus the square root of 592 all over negative 32. Alright, now let's work out the two different answers here. Pull up a calculator here. So first let's calculate 592, the square root. Where is that square? Oh yeah. On this calculator I have to do the power of 0.5. Okay, so the square root of that is 24.33. So I'll write my first answer is negative 20 plus 24.33 all divided by negative 32. And actually, let's work that out. So that would be divided by 32 negative. Now this one turns out to be negative 0.14. Okay, now that wouldn't make sense. We can't go backwards in time. What's happening here is that this is picking up that answer on the graph. And that doesn't make sense because back here, we haven't even let go of the ball yet. So the other answer is going to be negative 20 minus 24.33 all divided by negative 32. Okay, so let's work that out. Minus 24.33 divided by 32 negative. And we're getting approximately 1.39. Okay, so let's just double check that on decimals. Yep, about 1.39. Alright, so that may seem like it's a lot of work, but the main idea here is to find the ground where it hits the ground. You're finding an x-intercept. And it's a little more work because we can't factor. We have to use a quadratic equation to find them. Alright, then there's this one last thing that you should go over here that you should be able to do now. This is a nice trick. This is called the max-min trick. Okay? Now the max-min trick is if we have a parabola and we want to know what the absolute highest point is, if we want to know without graphing, the trick is that it is negative b over 2a over. And then we could go and figure out how tall that is. It would be some sort of height. So in this case, if we want to find the max, because this is a maximum situation, our graph is going up and hitting a max up there, then we'll use negative b all over 2a. In this case, negative b is negative 20 all over 2 times, and then we had negative 16. So we know the maximum is going to be when it's negative 20 all over negative 32, which, if I just do that on my calculator, 20 divided by 32, the maximum is going to be at 0.625 seconds. Now that tells us how many seconds until we reach our maximum, but it's not actually telling our maximum. So what we have to do then is go back and plug it in the original equation. So I will write y equals, and let me just write the equation again. Now if I put this in for t, I get y equals negative 16.625 squared. Okay, so now I have that all written in my equation, and I just have to figure that out, like using a calculator. So let me see here. Okay, now working on this on a calculator, I got 9.25. So just double check, make sure that you could find 9.25 if you put in a calculator. Now double checking on decimals, I got 9.25 and it's 0.625 over. Okay, so that is a projectile. Now there is another thing that could happen here. Okay, and it has to do with economics. So, sometimes max and mins in economics, you want to minimize the cost of something. So, for example, something that comes up in economics is, so this is the cost per unit, and this is the quadratic equation that models the cost per unit. Okay, and x, these x's stand for the number of units. Alright, so they might ask you a few questions like this. Like if we don't know much about the situation, but we have this model, we can ask, what is the cost per unit if we make 10? Okay, all this is saying is that x should equal 10. And then we should see what the cost of the unit would be. So, I take my equation, and I put in 10 for my units, and this will calculate the total cost. Now, I've graphed this in decimals as well. So this is my example here. And you could see that if I slide over to about 10, I get 183. Now, because I'm recording this, I'm doing this quickly, and on a test or quiz, you wouldn't be able to just slide over in decimals. You'd work this out, you'd work this chunk out first, and then that chunk, and then you would subtract and add, and you should get 183. Maybe this is dollars per unit. Okay. So in economics, this makes sense, or this happens quite a bit. Like it starts off at a fixed overhead rate of 200 to make 0. But then, because you're selling more and more, if you sell more and more of your items, it actually might be more efficient and easier to sell items in bulk. But then there are a lot of times when if you start to make too many, it actually costs more to make that much. So there's a sweet spot in there, and it's being highlighted right now. And if you remember, the min-max trick will be able to get us to that point right away. So the question might be, what is the minimum cost per unit? Okay, and that trick is negative b over 2a. So in this case, b is negative 2, so we would put positive 2 over there, all over 2a. So that'd be 2 times 0.03. So this really would be 2 over 0.06. If we go to our calculator, 2 divided by 0.06, that gives us 33.33333, or 33 and 0.3 repeating. So if we make about 33 units, that's going to minimize our cost per unit. Now that's not actually the cost per unit though, that's the number of units. So to figure out why, we would go back and calculate 0.03, and maybe to make things a little easier, we can round the x to be 33.3. Alright, so I'll work this out in chunks. Like that right there, 33.3 squared times 0.03, 32.2, let's just round that to be 33.3. minus, this would be 66.6 plus 200. So I'm getting around 166.7. That's the cost per unit, maybe dollars per unit. Okay, so this uses the same principle, except this time our parabola is going down this way, so we're interested in that minimum right there. With parabolas, it's the opposite. We want to know the highest right there.